Previously, we learned how to multiply polynomials. Take 4x times the sum of 3x plus 5, for example. We use the distributive property to multiply 4x times 3x to get 12x squared, and also to multiply 4x times 5 to get 20x. To factor the polynomial 12x squared plus 20x, we reverse the previous steps and determine what factors were multiplied to obtain this result. This process is called factoring the polynomial. The first step is to find out whether its terms have any common factors. To determine whether integers have common factors, it is helpful to write them as products of prime numbers. One way to find prime factors of a number is to use the division ladder. A prime number is only divisible by 1 and itself. For example, if we wanted to use the division ladder to prime factor the number 210, this is what we would do. We're going to put the number that we're trying to find the prime factor under a division symbol, and we're going to work upwards, performing repeated division by prime numbers until the final quotient is a prime number. So for example, the number 210 can be divisible by 2, which is also a prime number. So 210 divided by 2 is going to give us 2 goes into 2 once. We subtract, bring down our 1. 2 does not go in the 1. Bring down the other one. 2 does go in the 10, which gives us 105. And like the instructions say, we're going to perform repeated division by prime numbers until our final number is prime. So now we're going to divide the number 105 by a prime number. A prime number that I can think of would be the number 5. 5 goes into 10 twice and into 5 once, which gives us the number 21. We're going to keep on repeating our division by prime numbers until our quotient is a prime number. So the number 21 can be divided by the prime number 7. 7 goes into 21 3 times. And 3 is a prime number, so this would be our ladder. So the prime factors of the number 210 include 2, 3, 5, and 7. Now later we'll use these prime factors to help us find the greatest common factor. But let's practice. Let's find the prime factors of the numbers 42 and 90. So we're going to do the same repeated division by prime numbers until we're finished. So again, the easy number to always start with usually can be 2. Especially when you're working with the even numbers. So 2 goes into 42 21 times. Again, we want to perform that repeated division until our number is prime. The number 21 can be divided by 3, which will give us a result of 7, which now our quotient is a prime number, so we would be finished. So 2, 3, and 7 are the prime factors of the number 42. Now let's find prime factors of the number 90. The first prime number that I would think of would be 3. 3 goes into 90 30 times. Again, we want to perform that repeated division. I can divide 30 by 3 also, which would give me the number 10. Repeated division. Number 10 can be divided by 2, which would give me 5. So now I have a list of prime factors for 42 and 90. And the reason we would do this is because we want to find the greatest common factor. To find their greatest common factor, we're going to multiply the common factors. So let's look at what factors they have in common. They both have a number 2 as a common factor. And they also both have a factor, number 3, as a common factor. So if we take the common factors 2 and 3 and multiply them, we get the number 6. And that tells us what the greatest common factor between 42 and 90 is. It would be 6. When there are no prime factors in common, the GCF can always be 1. So a strategy for finding the greatest common factor. You want to write down each coefficient as a product of prime factors, just as we did previously. Then you want to identify the numerical and variable factors common to each term. Thirdly, you want to multiply the common factors identified in step 2 to obtain the GCF. If there is no common factors, the GCF is 1. Now, how do you find the GCF of variables with exponents? Again, it is easier to term as a product. For example, what is the GCF of 9a to the 5th power and 15a squared? So just as we wrote the numbers in prime factorization form, we want to do the same thing again with 9 and 15. Now I already know that the common factor between 9 and 15 is 3. But we'll write it out anyway. We have 3 times 3, which gives us the 9. And we're going to write out a to the, so in long form. So it'll be a times a times a times a times a. We also want to do the same thing with 15. Some prime numbers that make up 15 would be 3 times 5. And a squared written out would be a times a. So now it's your job to determine what the common factors are, multiply them together to find the greatest common factor. So again, they both have a common factor of 3. They also have common factors of a's and a's. Now since they only have 2 a's in common, that means a squared can be the greatest common factor. So the GCF between these two terms would be 3a squared. Again, you're multiplying them together. 3 times a times a. A times a gives me a squared, times 3 gives me 3a squared. Now let's find the greatest common factor of some more terms. I have 15a to the 4th b squared and 90a cubed b cubed. What we want to do first is write the prime factors of the numbers. The number 15 has prime factors of 3 and 5. We want to break down the variable a to the 4th into standard form, a times a times a times a, and also b squared, b times b. We want to do the same thing with 90a cubed b cubed. Since we used 90 earlier, the prime factors of 90 are 2 times 3 times 3 times 5. Next, we want to break down a cubed and b cubed, which would be a times a times a, and b times b times b. The next thing you want to do is figure out which numbers and which variables they have in common. They both have the number 3, and they also both have the number 5. Now let's see how many a's they have in common. The first term has 1, 2, 3, 4 a's, and the second term has 1, 2, 3 a's. That means it's only possible for them to have 3 a's in common. Now let's look at the b's. The first term has 2 b's and the second term has 3. Again, it's only possible to have the 2 b's in common. So for you to see the pattern here, what's happening is we're taking the smallest exponent and using that as our greatest common factor. Hence, between a to the 4th and a cubed is the smaller one. Notice they only have 1, 2, 3 a's in common. With b squared and b cubed, notice that they only have 2 b's in common, which is also the smallest exponent. So now that I've circled everything that they have in common, it's time to find out what's the actual, multiply together the prime factors and see what the actual greatest common factor is. When we multiply 3 and 5, we get 15, and we multiply a times a, we get a cubed. And when we multiply b times b, so the greatest common factor between 15a to the 4th b squared and 90a cubed b cubed is 15a cubed b squared. Now let's do the same thing for the next one. The first term is 42s cubed t squared, and the second term is 63s squared t to the 4th. So again, the first thing we want to do is just look at the numbers. Let's find the prime factors of 42 earlier, 63, like we learned earlier using the division ladder. So the number 42, when we put it in the division ladder, the first prime number that I think of is 2. 2 goes into 42 21 times. The next prime number that I would divide by would be 3. 3 goes into 21 7. Since my quotient is a prime number, I know that I'm finished. Now let's do the same thing for 63. The first prime number that I think of here would be 3. 3 goes into 63 21 times. I would also divide 21 by 3. 3 goes into 21 7 times. Again, my quotient is prime, so I know that I'm finished. Let's see what the common prime factors are. They both have 7, and they also both have 3. When you multiply 3 and 7 together, you get 21. So we know that the greatest common factor for the integers here is 21. So now let's look at in the first term we have s cubed, which is s times s times s, and t squared, which is t times t. In the second term we have s squared, which is s times s, and t to the fourth, which is t times t times t times t. Now again, you want to see how many of these variables they actually have in common. The first term has 3 s's, the second term only has 2, so they can only have 2 s's in common. Only has 2 t's, the first term only has 2, the second term has 4, so again they can only have 2 t's in common. So since we already know the greatest common factor integer, our final thing to do would just be to multiply everything that we have found together. So we're going to take 21 and we're going to multiply it times s, which is s squared, and t times t, which is t squared. So the greatest common factor for both of these terms is 21s squared t squared. Now we will take the processes we have learned so far to factor out the greatest common factor from a polynomial. Here are some examples. The first example has the polynomial 8m minus 48. So our job here is to determine what is the common factor between 8m and minus 48. The first thing that comes to mind is the number 8. Since the second term doesn't have a variable, m would not be a common factor here. So if they both have the number 8 in common, in actuality what you're going to do is you're going to divide each term by what you find to be the greatest common factor. So when I divide 8m by 8, what happens is the 8's cancel and I'm left with an m. In the term negative 48, when I divide by 8, I get 6. So inside the parentheses, I'm actually putting the answers after I divide by my greatest common factor. So now I have factored the 8 to get the answer of 8 times the difference between m and 6. Now we're going to do the same thing for the next polynomial. We have 35a cubed b squared plus 14a squared b cubed. Again, the first thing you want to do is, what's the common number that they have? I know that 35 and 14 both can be divided by 7. So I'm going to want to take that out. They also have at least a squared in common and b squared. So that's also going to become part of my greatest common factor. Now notice that I put the GCF out here on the outside of the parentheses. That's your GCF. Once you find your GCF, what you have to do is divide both terms by that GCF. When you divide by the GCF, you're going to find the answers that belong inside of the parentheses. So take it one thing at a time. Let's look at the numbers. 35 divided by 7 is going to give me 5. A cubed divided by a squared is going to give me a, if you follow the laws of exponents, and b squared divided by b squared is just going to give me 1, so I don't need to write that. 14 divided by 7 is going to give me 2. A squared divided by a squared also is going to give me 1, and b cubed divided by b squared is going to give me b. I have factored this polynomial. Now to check your answer, to make sure that you factored correctly, what you should do is use your distributive property to check your answer. If you do not get back to your original problem, then you can know that you did it wrong. So let's just check. 7a squared b squared times 5a is going to give us 35a cubed b squared. And when I multiply 7a squared b squared by 2b, I'm going to get a 14a squared b cubed. Does that match my original problem? Yes, it does. So I know I factored correctly. Now let's look at a few more polynomials that we can factor out the greatest common factor from. In this first problem, 3x to the fourth minus 5x cubed plus x squared, the first thing I want to do is look at the numbers. 3, 5, and 1 do not have any common factors other than 1. So let's look at the variables. I have x to the fourth, x cubed, and x squared. Now the greatest common factor between these variables can only be the one with the smallest exponent. So in this case, the greatest common factor is x squared. Now again, notice I'm writing the greatest common factor here on the outside of the parentheses. So what's going to happen is I'm going to divide each term by my greatest common factor in order to find out what I should put inside the parentheses. So with the first term, 3x to the fourth divided by x squared, I'm going to get 3. The second term is minus 5x cubed. Minus 5x cubed divided by x squared is going to give me a minus 5x. The next term, x squared divided by x squared, is simply just going to give me the number 1. So now I have completely factored out all the greatest common factors from this polynomial. Let's try another one. In some cases, there won't be a letter or a number in common, but there's always at least the number 1 that these polynomials have in common. And most of the time you'll be factoring out a negative 1, like in this case. Notice how the leading term is negative. Usually that's a sign that you want to factor out that negative number. Now we also notice that they don't have any numbers in common or letters. So the only thing we really can factor out is a negative 1. Now again, if that's going to be my greatest common factor, you need to divide each term by that to find out what answers are going to go inside of my parentheses. So negative a cubed divided by negative 1 is going to give me a positive a cubed. A positive 2a squared divided by negative 1 is going to give me a negative 2a squared. And a negative 4 divided by a negative 1 is going to give me a positive 4. That would be my final answer after factoring out the negative 1. So basically what happened is I changed the signs of each term to its opposite. This negative a became positive, this positive 2 became negative, and this negative 4 became positive. Now for the third one. Negative 20m plus 30. Here again, there are no letters in common, but there is a number 10. But instead of just factoring out 10, I'm going to factor out a negative 10, mostly because the leading term is negative and we just want to get rid of that. So, since the greatest common factor is negative 10, I'm going to be dividing both terms by negative 10. Negative 20m divided by negative 10 is going to give me a positive 2m. Positive 30 divided by negative 10 is going to give me a minus 3. And that's going to be my final answer. And again, you can always go back and check to see if you did it right by using the distributive property. Negative 10 times 2m gives me a negative 20m. Negative 10 times negative 3 gives me a positive 30. That's how I know I did everything correctly. In these next two problems, factoring out the greatest common factor is going to look just a little bit differently. It's important for you to understand that terms are separated by plus and minus signs. So in fact, this whole thing is my first term, and this whole thing is my second term. Within this term and this term, I can see that there is a common factor. That common factor would be x plus 4. So since they both have the common factor of x plus 4, the same way before we were taking out the GCF, we're going to do this. So if they both have the common factor of x plus 4, what's going to go inside the parentheses after we divide? Because again, just like before, you divide by the GCF. If I divide this term by x plus 4 and this term by x plus 4, what happens? The x plus 4's cancel in both terms, and you're only left with what they were being multiplied by, which in this case was the x and the 3. So here I have factored out the greatest common factor, x plus 4, and this would be my final answer. Again, you could use the distributive property to check and make sure you did everything correctly. Let's do the same thing for this next problem. Again, notice that 2y times the difference of y and 1 plus 7 times the difference of y and 1 are separate terms. This is your first term and this is your second term. So it's up to you to look inside the terms to see what is common about them. They both have the y minus 1. So the y minus 1 becomes your greatest common factor, and you want to pull that out. Now, since that is your greatest common factor, what you're really doing is dividing by y minus 1. So again, just like in the previous problem, the binomials cancel and you're left with 2y plus 7, which gives us, and this would be my final answer. Now we are going to use this to help us factor by grouping. Here are the steps to factor by grouping. First, you want to group the terms of the polynomial so that the first two terms have a common factor and the last two terms have a common factor. Secondly, you want to factor out the common factor from each group, just like we did in these. Thirdly, you want to factor out the resulting common binomial factor. So let's look at these steps and put them to action. One way to tell that you should factor by grouping is if the polynomial has 4 terms. So here are 2 examples of polynomials with 4 terms. So just like the steps said, we want to group the first 2 terms and the second 2 terms together and factor them separately, because all 4 terms, 1, 2, 3, 4, don't have something in common. These 2 have something in common, these 2 do, but all 4 of them do not have one thing in common. And that's why we're going to group. We'll group these 2, take out a common factor, group these 2, take out a common factor, and finish like we did earlier. So in the first group, 2x cubed and x squared, the common factor here is x squared. So when you divide this by x squared and this term by x squared, your result will go into these. 2x cubed divided by x squared leaves me with 2x. X squared divided by x squared leaves me with 1. Now we move on to the second group. What do 12x and 6 have in common? They have the number 6. When I divide this term by 6 and this term by 6, I should get the same result that I got in the previous one, which was 2x plus 1. That's what I need in order to finish the problem. So 12x divided by 6 definitely gives me 2. Divided by 6 definitely gives me 1. So now I have 2 terms with, instead of having a number or letter in common, they have a binomial in common. So we're going to factor out this common binomial by putting it in parentheses here, 2x plus 1. And what goes in the second set of parentheses is what's left in the problem, the x squared and the 6. So here I have factored out this polynomial with 4 terms by grouping. Now let's look at the second one. 2c minus 2d plus cd minus d squared. Again, what you want to do is you want to group the first 2 terms, group the second 2 terms, and factor out the GCF individually. In the first binomial, the GCF is the number 2. So when we factor out the number 2, it goes on the outside of the parentheses. On the inside goes the answer. 2 divided by 2 gives me 1. That's going to cancel. It's going to leave me with C. Minus 2d divided by 2. The 2's are going to get canceled, and it's going to leave me with minus d. Now again, this is a hint to tell me I need my second set to at least have c minus d as a factor. So let's look at cd minus d squared. The common factor here is a d. So when we factor out the d, let's see what's left. The d goes on the outside as my GCF, and my answer is going to go inside the parentheses. CD divided by d, the d is with c, and minus d squared divided by d is going to leave me with a minus d. Again, I did a good job because I have matching binomials here, and again, that's going to be my greatest common factor. So what we're doing is we're taking out the greatest common factor more than once. We took out a greatest common factor here and here, and now that we're at this step, we see that we have another common factor. So again, the common factor c minus d gets brought down, and what gets put in the second set of parentheses is left, the 2 plus d. Now let's try 2 more problems like this. Now we have the polynomial x squared minus ax minus x plus a. Again, same as before, we want to group these terms in groups of 2 and see what factor we can take out. In the first binomial, x squared minus ax, we can factor out an x. So after we factor out the x, let's see what's left. X squared divided by x leaves me with x, and minus ax divided by x leaves me with minus a. So now I know, again, that I want my second set to have a binomial factor of x minus a. So when I look at the problem, I can see that what's left is very similar to what I need, but it's not exactly what I need. It's minus x plus a. It's the exact opposite I need. So what this tells me is that I need to factor out a negative 1 so that the signs inside of here will change and match that exactly. So when I factor out a negative 1 from both terms, I'm left with negative x divided by negative 1, which is a positive x, and a divided by negative 1, which is a minus a. Again, I have the common binomial factor of x minus a, which is going to be my first factor, and what's left? X minus 1. Just factored this 4-term polynomial by grouping. Now let's try that same technique again with the one more problem. I have 7x minus 7y plus xy minus y squared. Again, you want to group these terms in 2s and factor out the greatest common factor individually and keep going. In the first binomial, I can see that the common factor is 7. After I factor out the common factor of 7, I'm left with x minus y. Let's look at the second set. xy minus y squared, I can see that the common factor here is y. So after I factor out the y, what's left? xy divided by y leaves me with x, and negative y squared divided by y leaves me with minus y. Again, I can see that out of my 2 terms, here's my first term, here's my second term, that they have the common binomial of x minus y. So when I factor out x minus y, there's 7 plus y. And this would be the answer of the in factored form.